Good morning, everyone. My name is Kovida, and today's topic roll number 22951A3338. Today's topic is about inclusion, exclusion by ordering fee cancellation. Introduction. Let omega AU be a measure space, B be a finite index set, and alpha PP family of measurable sets. The formula is given below. Is known as the principle of inclusion exclusion, where AP bar is the complement of AP. The principle of inclusion exclusion is a classic counting technique in combinatorics and has been extensively studied. Since the sum on the right side of equation 1 ranges over a large number of terms, it is natural to ask whether fewer terms would give the same result. That is it possible to reduce the number of terms by predicted cancellation? Lots of the answers to this question has been given by several authors. A well-known example is the one given by Whitney in 1932 for the chromatic polynomial of a graph, which states that the calculation of chromatic polynomial can be restricted to the collection of those sets of edges which do not include any broken circuit as a subset. Various cancellations from the inclusion-exclusion principle were given from the perspective of both combinators graph theories in literature. Narushima presented a cancellation for the inclusion-exclusion principle depending on the prescribed ordering on the index set P. This result was later improved by Doman. Using the same technique, Doman also established an abstraction of Whitney broken circuit theorem which do not apply to the chromatic polynomial but also to order graph polynomial. Cancellation methods for inclusion-exclusion principles strongly depend on the prescribed ordering on the index set P. Method which do not require any ordering on P. Our methods extends all the ordering-based methods given in the previous literature in general and reduce more terms. As examples, we choose our ordering-free method to improve results on the chromatic polynomial F hypergraphs and dependency polynomial and domination polynomial of the graphs. Inclusion-exclusion by predicted cancellations. Second, inclusion-exclusion by predicted cancellations. For a subset of a post-set partial set P, let P denote the upper set bound of P which are not in B, that is. In 9, Narushima presented a cancellation for the inclusion-exclusion principle on the semi-lattice. This result was later extended to many forms. The following one was given by Dobbin. Theorem 2.2. Let alpha A nu be measure space P be a post set and AP we include a family of measurable sets. If X P is a class of subsets of P such that we know that Bi is empty when Bj Pi belongs to Pi. For some j is less than I, since there is no I that satisfies the requirement, we now give our main results which does not require by ordering on P. Theorem 2.2. Let nu be a measure space, P be a set and AP be a family of measurable sets. Let P naught, I naught, P2 to P2 star, Pk, Pk star be the pairs of subsets P. If Pi belongs to Bi star is equal to phi, then Proof. Let I belongs to P, then I belongs to Pi for some I belongs to 1 to K. We claim that such Pi is unique. In fact, suppose to the contradictory that I belongs to Bj, and with no loss of generality that J is less than I, then by the definition of Pi, I less than Bj. This contradicts that I is to Bj. As a result, Pi be to Pk. This is a contradiction because our claims follows. Then, where the last equality holds by the principle of inclusion exclusion, notice A par P is the complement of P. Since, therefore, 3 examples in graph polynomials. G. Example in graph polynomials. As examples in this section, we applied theorem 2.2 to chromatic polynomial of hypergraph dependence and domination polynomial of graph. We will see that the ordering free method requires more terms than the ordering based method. Be a graph polynomial of a graph G represented in the form of inclusion exclusion principle, i.e. let Pgx belongs to where each of G is the edge set of G and P f of x is a polynomial of x associated with f belongs to E of G. We specialize the index set B to be E of G and for any. Thus, a pair satisfies the requirement of theorem 2.2. Provided it satisfies, we refer such a pair P belongs to B as a broken pair P G of x, and B, a broken set of P, is minimal. B, that is P, has no proper subset satisfying. Further, given a linear ordering, we call B a broken set with respect to if P belongs to B. By theorem 2.2, we have the following corollary immediately. Corollary 3.1. Let Bi of Bi star B2 B2 star and to Bk Bk star be broken pairs of Pg above x P of Gx, then chromatic polynomial of hypergraph. The chromatic polynomial x h of x of a simple hypergraph h counts the number of vertex coloring such that each hyper edge of coordinatory at least 2 has 2 vertices of distinct colors. The following inclusion expression was given in where C of x is the number of components of the spanning subgraph of H with the edge set of F. Given a linear order less than on the edge set E of F domain, generalize the Whitney broken circuit theorem to hypergraph by extending the broken circuit to a circle with a particular constant that each edge of the cycle is included by the union of the other edges of that cycle. A set F is called a omega circle if F is minimal such that for each we know that every cycle with the above particular constant is or contains a omega circle with while a omega circle is not necessarily a cycle with this constraint. A set B is called a broken cycle if B is obtained from a omega cycle, deleting its maximum edge. For B belongs to E of H and B belongs to E of H by B by 9, it can be seen that B is a broken set of H x of H, x provided B is minimal such that we can see that the notion broken set for hypergraph is an extension of broken circle. Moreover, in condition there is no need to require B to the maximum edge of B for a broken set. Let us consider a hypergraph H is equal to VE with a vertex set V is equal to 1 to 6 and edge set E with 1 to 3 subset 3 4 5 subset 2 3 4 subset 1 to 6 subject. We know that H contains neither broken circuit nor broken cycle, no matter how its edges are ordered. This means that no terms in H can be reduced by broken circuit or broken cycle. For an edge ijk, we write it simply as ijk. By 10, it can be seen that H has two broken sets Pi is equal to 1, 2, 3, 3, 4, 5 with P1 star is equal to P1 flow brackets is equal to 2, 3, 4 and B2 is equal to 2, 3, 4, 1, 2, 6 with B2 is equal to B2 star is equal to 1, 2, 3. Consider the edge ordering 1, 2, 3, 3 less than 3, 4, 5 less than 2, 3, 4 less than 126. By again 10, H contains only one broken set with respect to less than, that is P is equal to 1, 2, 3, 3, 4, 5 with B dash is equal to 2, 3, 4, thus X bar is equal to B. So by theorem 2.2 and corollary 3.1, the chromatic polynomial HH is given below. Dependence polynomial of graph. For a graph G, the dependence polynomial of G can be represented as the following inclusion formula, where Gf is the number of vertices in subgraph of G in use of F. It was shown that the Whitney broken circuit theorem is also valid for dependence polynomial by 9 and 11. A set B of edges is broken set provided P is minimal such that G of P is equal to GU capital P union B for some B belongs to P. Let us consider the part G of length 4 with edges. Similar to the previous example, we have width and weight, and therefore the following is provided. Domination polynomial of graph. For a graph G and W belongs to VG denotes by n of W. Close neighborhood of W, that is n of W is equal to W belongs to V's colon U is adjacent to some vertex in W. Let Di be the number of sets W of I vertices such that Ng is equal to Vg. The domination polynomial dgx is defined by d of gx. The following form was given in a set B is called broken neighborhood if B is equal to NV and V is equal to max NV. Infer, domain and determinant prove that the sum in 12 can be restricted to those subset of vertices which do not contain any broken neighborhood. Due to 12, we replace the role of edges in 9 by vertices for B and minimal such that we can see that the broken set of T of Gx is an extension of broken neighborhood. Consider the part P, V1, V2, V3, V4 with vertex ordering V1 is less than V4 is less than V3 is less than V2. Similarly, by 13 we have V1 is equal to V1, V3 by P1 star is equal to V2, P2 is equal to V1, V4 with P2 star is equal to V2 and B3 is equal to V2, V4 with B3 star is equal to V3 and X is equal to V1. Therefore, B1 is equal to flower brackets of subset V1, V3, subset of V1, V2, V3, subset of V1, V3, V4, subset of V1, V2, V3, V4, close brackets. And B2 is equal to subset of V1, V4 and subset of V1, V2, V4. And B3 is equal to V2, V4, subset of V2, V3, V4 and The total is equal to V1, V3, V1, V2, V3, subset of V1, V3, V4, subset of V1, V2, V3, V4, subset of V1, V4, subset of V1, V2, V4 is equal to B union of P1 union of P2. Thank you.